Hi. So I wanted to, well, I have been researching autonomous vehicles, current technology. I wanted to see what the current state was and see if I could throw together a test bed or, an A/B comparison type setup to where when my algorithm is capable, that I would be able to compare it against current technologies. But in doing that research, I came to realize that it'll probably take me about three months or so. It's fairly complex, so it'd probably take me like 3 months to build. I was hoping for just something I could find on the internet and set it up and test it and play around with it. But they're very tailored, very specific, and I'm going to go into the details about that here in a minute. And so for the next 3 months, I want to focus on my own algorithm because it's the holidays, and so I should be able to get um, more dedicated time to that algorithm to hopefully make some good advancements. So, anyway, let's talk about current technology in autonomous vehicles. So, we have the basic steps or functions. So lane detection, object detection, sensor input, calculating trajectories, and then determining what action to take. So the first step in determining lanes, there's two different approaches, but the biggest one I found is basically just mathematical computations. So basically, they say, let's take a section of the image and try and find the lines within that section. And then those lines we'll assume are the road lines. And the first thing you need to do is you need to correct for lens distortion, and then you have to convert that to a two-dimensional plane. So you have to remove the projection, i.e., the 3D, and then you have to identify the lines and then convert it into a mathematical formula, which then gives you a mathematical representation of those lines, which you can then do math on. Problem number one, you have to calibrate it to the given camera. So this is very specific to a specific camera. The second issue is the box you draw. That's a static fixed input, which means if your car is hitting a bump, or it's slowing down or accelerating, or there's a hill coming up, or you're going down a hill, that box is not moving, but the visibility of that road is all over the place in those scenarios. So this becomes not that great of approach. The other issue is that what if the lines go outside your box? In this example, the box is pretty narrow for how wide the road is. The road is quite wide in this image, and so you're not calculating the complete line. Granted, it's enough to get the job done, but and then the other issue is, what if there is no lines, or the lines are faded, or it's concrete and you're looking for the white lines on the concrete? So there's blending happening that's hard to separate the two. It's not as black and white as the algorithm would like it to be able to detect where the road lines are. And so this approach, while potentially capable, is definitely very limiting. So the other approach is to use deep learning, and you have a bunch of labeled data telling you where the edge of the road is, telling you what type of line it is, telling you if it's a turn lane. The problem here lies within, well, again, what if you don't have lines? Now, I did see another image. I wasn't able to find it when I was building the PowerPoint, but I did find one image that showed the dirt edge of the road, and it said that this is the edge of the road. But again, that's labeled data, so somebody went through it and said this is the edge of the road, which labeling enough data to make sure that you capture all driving conditions. You got snow, you got rain, you got dirt roads, you got well paved roads, you got concrete roads, you got very visible lanes and lines, you got reflective lines, worn out and faded lines. And what if you're in a construction zone and they got those little flappy things on the ground so you can barely tell where the line is? Or they don't even have those because they haven't put them down yet. So creating a training set to be able to capture all of that information is a lot of work. And I did find a training set, but they wanted money. And I don't have any money to just play around with this stuff at this point in time. So that's where lane detection is. I mean, if you use a combination of both, you might be able to capture a complete picture, and then that complete picture will, the overlap of the two should be able to eliminate errors, if you will. One would hope anyway, but it would still be a lot of work to build both of them. And then the next step is object detection, which this is fairly complete solution, I want to say. There's plenty of training sets out there. It's mostly free, and the models that worked at identifying these seems to work pretty well. And then they're readily available, free for the most part. So this space, I mean, there is some issues with like it's a plastic bag blowing across the street instead of a cat running across the street, and it'll say, well, it's something we should stop for, even though it's a plastic bag. But I don't know if that's a big deal. I'd prefer to stop over it saying, oh, it's a bag and running over a cat, so that wouldn't be good. But object detection in this space seems to be pretty robust and works pretty well. And then we have our sensor array outside of the cameras. Now, I don't include LiDAR in this at this point in time. So you got the sonar, which is the parking sensors, and then you got the radar, which is the front facing, detecting cars and adaptives, cruise control. These sensors to me are like the failsafe. If our object detection didn't work and it didn't calculate the proper distance of a car, and it didn't calculate how fast we were coming up on that car properly, the radar will pick up that car and say, whoa, we're coming up on that car really fast, stop the car. Same with the sonar sensors, the parking sensors. You can use those for detecting cars next to you. So if you think about changing a lane, it'll say, well, there's a car there, don't change the lane. So it can override the camera identification of everything and make sure that it's still safe. It's a second layer of protection, if you will. And so the next step, once we've identified the lanes, once we've identified cars and traffic lights and pedestrians, then we calculate the trajectories of everything that's moving. And the reason we'd want to do that is to be able to calculate a window of opportunity. Can we merge into traffic? Can we make a left-hand turn? Can we make a right-hand turn? Is this person going to step off the sidewalk, or are they stopping and going to let us go by? So that's what calculating trajectories gives us. Now, trying to calculate trajectories off of camera work is very difficult. So now we're talking about a 2D image, trying to determine where things are moving to. And this is kind of where LiDAR comes in. So if LiDAR is being used, you can get a 3D representation of it, and based on the frames, you can calculate the trajectory of the moving objects within that sensor array. But LiDAR is really expensive. So how do we get around that? And that's kind of the question. The car industry believes that the more people use LiDAR, the cheaper LiDAR will become. It's not really proving to be true. They're still pretty expensive pieces of equipment. I don't know, time will tell, I guess. I mean, they have come down in cost, but they're still exorbitantly expensive. comparatively. So that's calculating trajectories. And then we just determine what action we're going to do based on all those calculations. Where, what is our destination? What lane do we need to be in? In this particular animation, it's trying to avoid construction cones. So identified construction cones on the side of the road taking over the lane, and it determined that it should, shift over to another lane. I was trying to find a video where object detection becomes a problem, which I guess I want to backtrack a little. But there's a guy, and this is Waymo. So Waymo has a video talking about their hurdles and the problems they face. Like somebody running a red light. Do we stop? I mean, we have to detect that car that's about to run that red light. And this goes back to the trajectory calculations. You can determine that this person is not stopping for the light. And based on those trajectories, it looks like it'll collide with the car. So the car will come to a stop to make sure that person running the red light will miss the autonomous car, even though the light is green for the autonomous car. So another issue is a bicyclist riding on the side of the road with a stop sign strapped to their back. It's an odd scenario. I mean, I've never honestly seen it personally, but apparently they ran into it, so they needed to do something about it. And I guess they determined that if it's in motion and it's not at an intersection, then it's not a valid stop sign, I assume. Or maybe they, since Waymo's approach is to model the entire city that it's driving within, they probably said, well, this is not a location where a stop sign exists, so we're going to keep moving. But what if this is a construction site? Just like this animation. What if there's a construction worker that's controlling traffic and they have a stop sign? Do we detect that and stop for that given scenario? I believe they do. So, you have to build rules. Or, I mean, they could be using machine learning at this level. If you have a complete model of your environment, you can simulate every scenario, and you can get the machine learning to develop a robust enough solution to drive the car around. Again, you just use the hard sensors to ensure safety. So if I'm about to collide with something, I'm going to stop the car. I don't care what machine learning is doing, we're stopping the car. But I'm not 100% sure, because they make the comment that they're using machine learning as much as possible, but when they can't use machine learning, they have a bunch of rules and logic to control a car. So it's definitely a mishmash of both. They're not fully embracing machine learning to completely drive the car. So that's that slide, and then we'll talk about the failures, which I don't have a good failure. There's plenty of videos on YouTube, even in 2019, showing failures. Like one of them, the road that it's supposed to be on glitches. I guess the GPS data glitches or something, and it shifts the road like 4 feet to the right, and the car jets over into oncoming traffic. I mean, that's seriously unsafe. It's like, there's another one where it didn't see the construction concrete barrier for some reason, and it slammed right into it. And it's like, why didn't you use your front-facing radar to override any machine learning to stop the car? So there's still a myriad of problems to be solved. Like the picture I have here for detecting a lane. That's just one example right there. It's like it can't even find the lane properly. So how do we overcome these problems? They believe that a combination of, an aggressive sensor suite, i.e. including a LiDAR, and modeling the entire area, this is Waymo's solution, that And I believe it's Uber's solution, because I believe Uber is mapping everything where all the Uber cars drive. So this seems to be the approach that they want to solve the problem. They do a complete model of the environment, and then with that simulation, they can train a machine learning algorithm to drive within that environment. As long as the environment doesn't change, they should be good to go. Like the previous slide, I have construction. There's a construction event going on. Maybe they change the entire road, and Waymo takes a while to update their maps, and their car believes that that lane still exists, and they drive over the sidewalk or whatever it became. So there's definitely hurdles to creating a virtual representation of an area. The other hurdle is you're talking about creating a map of everywhere a car can potentially drive, which is a huge hurdle. And then you have to store all of this information, and then you have to create machine learning to drive every possible scenario that you can think of. And of course, you can't always think of every scenario. What if, you have these people that are trying to trick facial recognition programs? People go out of their ways to screw with technology. And how do you combat that? How do you keep people from screwing with these autonomous cars? That's another question. What about theft? So that's what the purpose, these hurdles are reminding me exactly why I went down this path of trying to build my own AI algorithm. It's like looking at a neural network. How do I train a neural network without knowing the answer to the problem? Because you model your city, you create all these training scenarios that you could possibly think of or have experienced. Then you go and train your algorithm. I mean, you're basically creating the environment. You're creating all the answers to the situation before they even come up. And then on top of that, once you train the machine learning algorithm for all of this stuff, it still can't handle an unexpected event. And that's what the purpose of this other picture is, with the guy bicycling and turning in front of the autonomous car, the Waymo car. A neural network can't handle an unexpected event. And so how do you create an algorithm that can deal with these scenarios? Unexpected events, learning on its own. Reinforcement learning tries to answer the learning on its own, but you're still creating a ruled-based environment to train to create the reinforcement learning algorithm. And so you're still pouring your knowledge into this algorithm to make it work. How do you get an algorithm to think on its own? How do you get an algorithm to deal with the unexpected, the unplanned, the unknown? And that was the driving force for me to come up with the algorithm that I came up with. And I believe it solves those problems. Now, granted, we're still in the unproven phase, which is a hurdle for stuff. And I believe it's the hurdle why I'm probably not getting investment capital. So, whatever. That's why I want to focus on trying to get the algorithm moving forward over the holidays. I mean, that was the plan anyway, but I've been on this detour for the self-driving car for a little while that I wanted to make sure I wasn't missing anything. And I think I'm missing some things on my pitch deck that could probably be refined from a pitch perspective, contrasting this versus my algorithm. But for the most part, this captures it. I think this captures the current state of the technology, what the limitations are, what the hurdles are, how to improve the technology, where it needs to be improved. And so, anyway, if you got this far, I appreciate watching. If you have any questions, concerns, you want to make comments about this video. Also, if you want to check out my other videos, I have a full playlist of AI centered around my algorithm. And then, of course, I put up some videos. I moved some videos from my other channel to this channel that are basically my resume coding projects that I've worked on in the past. Anyway, if you found this useful, thanks for watching. Till next time.